Hello everybody, my name is the CrabBG and today we're going to continue checking out Java's bytecode. So in the last episode we got some logging working, which I've moved on to a different folder, moved it to a different folder. So now if we run it, it now accepts the program. So what we can do is probably now disassemble our original program from episode 1. So we get this, right? So we get some stuff in here, right? We have get static, some push hello world, an invoke virtual, a return, and that's for the main function, right? So we've already parsed everything and we're kind of logging it, which would be very useful because now I think we can experiment by maybe starting to generate some Java bytecode. So how about we actually do that? So I think that this tool is going to be specifically useful for that. So let's actually create a folder, call it maybe something like hog. Hog is the name I chose, and as you can see, it's very random. I just ran it through an animal generator, and we got that for a name. So I guess we can use that. So now let's actually make the actual project. So we do cargo init, and if we open up our editor, which I have open already, but it shouldn't really be open, right? Source main rs, right? And we get hello world, right? So how about we log something like hello hog? So that would be just a case of doing this, right? And we get hello hog. Alright, so let's actually start by going back to the Java documentation for the virtual machine specification, right? And let's check out some of the structure for the file. So the class file usually starts with the magic number, right? So let's actually open up some sort of path. So we can call this something like opath, which is going to be equal to, I don't know, maybe output.class. So then now what we can do is just essentially take this and just read all the bytes with standard fs read opath. And if it fails, or actually not fs read, right, we want to kind of open up the another stream for just that, right, for writing. So let's actually go rest of the docs and see what we get in here. So we have, all right, the programming language was my example, extensive API, right? Let's actually go here. And how do we open a file? Well, I imagine that there's probably some sort of function that's called like fsopen. And what do we get? We get standard fsopen, right? So what can we do? Well, we can just do something like maybe create. That actually seems a lot better than open, right? Because we want to create a file, a new file to output to. So let's actually do that. So we have f equal to file create. And that's probably standard fs file create, and that's going to be opath. And imagine that can fail, so how about we just expect it? So expect it doesn't fail, right? So now we get that, and we probably can now write something to it. So how about we just write hello world to that file, close it, expect that this would work, and that's it. So let's actually just do that. So if we run our program, what do we get? Well, first of all, cannot write into file, right? Into a file. So now we need to do must implement IO write. Let's actually use standard IO write. Let's do that. And let's first of all clear the screen and then run it again. And what do we get? We get a file named output.class. And if we open it up in our editor, we get, as you can see, we're editing this, hello world. So now let's actually just take what we have here and let's just open up our sort of thing in here and just, well, right, this isn't really what we want because we're working with binary files. So maybe we need to do something like out, right, which is going to be a vector of bytes. And can we make a vector of bytes out of some sort of characters? Well, yes, we can actually. So that's going to be a binary string. A binary string is just a string that's like an ASCII string, like what you would have in C, right? So now if we do toOnt, we should probably get the output. And if we take this and write it to the file, I think file has some sort of like write feature. I'm pretty sure. Let's actually open it up. So that's right. Standard fs write. So now we have standard. Well, not really, right? We don't want to do that. We want to do standard fs file, right? What does it implement? Does it have write? It does have some sort of write. Maybe there's a function called write. Okay, so yeah, write all. That's what we want. So we do write all. We reference out, and we expect that this would work. Like it's pretty fair to expect that this would work, right? Error cannot write to file. So this would fail only if there was something like, for example, permission error, right? You can't create files, which in this case is not what we want, and that's kind of like unexpected behavior. So yeah. And if we run it again, we have mismatch types, right? So we need two vector, right? It's not toOnt, it's two vector. Okay, makes sense. All right, now we get some bytes, and if we open up output class, we get hello world, right? Makes sense. So now we can generate these output bytes and actually write them, right? So what can we do? Well, let's actually start by just creating an empty vector, right? And then to that vector, we can append some bytes, or maybe just extend, right? Extend by some bytes. So those bytes are going to be ka, fe, pe, pe. But now we need a vector of bytes, right? We need to turn this 4-byte number, right? 4-byte number, which is U32, right? And let's actually have a distinction. U32, right? We need to convert this to some sort of array of bytes, which, right, we want to convert it to this, right? And how do we do that? Well, it's pretty simple, right? We just have to use a feature that's called toBytes. For 2 bytes, let me just 2b bytes, I think it was big endian bytes. Yes. So now if we go to, for example, U32, 2b bytes or 2 lebytes, and we get this array, right? Make sense? It should make sense, right? So let's convert it to b bytes, and now we get some sort of bytes and we extend it, right? Well, we need to make output mutable. That makes sense. And what do we get? We get the output, which is the magic number. Right? So if we open up output.class, we get a lot of weird characters, right? Because some sort of weird thing, but that should be cafe babe, because if we convert this to, of course, lowercase or uppercase, it doesn't matter. I feel like uppercase is a little bit easier to read, right? We probably can just do something like const java magic to kind of abstract it away, which is just u32 equal to this, right? That makes sense. So that's Java Magic. So that's Java Magic to be bytes. And now, what else do we need to do? So I guess we can actually try running this program through our disassembler. So let's actually start another CMD session. Or actually not here, but we want to start another CMD session on this side. So we have both of them. Probably best if we just had this and this. Right, they're just two tabs. So now what we can do is just run this one through the disassembler. So we need to do Disassembler, Java disassembler, and now we can just do cargo run. We want to run this on the last folder, so we go back to this directory, and then where do we go into it? Into hog, the hog directory, and then we want to read output.class, right? So we get an error, right? We get an error. At split index is 2 should be underscore length. So we definitely passed the verification check for the Java Magic, right? How about we now move on to the next part? So it's a minor version and a major version. I don't think minor and major versions matter, but we can just do something like Java minor, which is going to be a U32, U16, was it? It was U16, yeah. Java minor version, which is going to be 0, and then we have the Java major version, which is also going to be 16. That's 55. I don't think this really matters. It's probably going to work with a lot of different versions, but that's what we get. So now we can do extend by Java minor to be bytes. Right. Everything is big ended, by the way. To major. Alright, so now we get that. And we kind of want to generate some sort of file that's really like basic. We don't want anything too crazy, right? And how about we actually write some message like successfully, like this info successfully wrote to OPAF, right? And that should be it. And if we run it again, not this, but this, we have successfully wrote to output.class. So now we get the new output, and we need more information. So we need more stuff. So the first thing we need is the constant pool count. So the constant pool is actually always at least 1 for Java, and I think the Java virtual machine expects that. But in this case, since our disassembler doesn't care too much about it, we can just kind of write nothing. So that's constant pool count, and that's going to be equal to another, probably just U32, U16 actually, and that's going to be equal to 0, right? So then we can extend that by constant pool count to be bytes, right? And then we get that, and then output extend with, so the constant pool is empty, so we don't really have to bother about that. Well, actually, right, it's 1, because if it was 0, then this would be invalid, right? And it would overflow and a lot of bad stuff would happen. So we have that. Now we need to write the access flags, which, I mean, we can just write whatever we got at the start, which, by the way, we can open. We can open up the old one, which was the debug.log, and get the information, like for example the access flags, right? So these are the access flags. We can just copy them. I don't know what they are, but there's something, right, that we just kind of don't care about too much. Bytes. But we explicitly want to say that this is right, we want to explicitly say that this is in fact U16. So we just do that by saying U16, right? And those are the access flags. Then what do we have? Well, we have the this class and the superclass, which are all required indexes. Well, okay. We expect that this exists, right? So we need to now add more elements to the constant pool. Right. Well, let's actually run this to here and see what happens, right? Let's see if it works and where we break. We probably just break at the exact same place, right? Because, yeah. So essentially, we the length was 0, right? We expected more, but the length was 0. So we parsed everything up to this class and superclass. So now we need to add more elements to the constant pool, which I guess now it's time to actually abstract that away. Remember how we had this in here in the Disassembler? If we open up main, right, we had this from bytes, which read the entire thing. Well, imagine that, but in reverse. Right, so instead of reading the bytes, you're actually writing to the bytes. So what would happen is probably, right, you have two options for what you can do with design. You could do something like 2 bytes, which would just return something like a vector of bytes, which, right, it's a way to design the API, definitely, but I don't think it's too efficient. I feel like it's a lot easier if we had a vector of byte that we can extend, right? So now that we have this, we can probably copy a lot of the code. So something like const info, right? And copy this and go back to source main rs and kind of paste it in here, right? We have UTF-8 and let's actually implement const info. Do something like do bytes, which what it would do, take a self and it would take some sort of bytes array that it can actually extend, right? And what we want is to kind of add match the self and do different stuff to it, right? So let's actually open up the docs that we have in here. Let's open them up. So yeah, that's basically the existing pages here. So we want to do constant, and for right now we just need a class and we have an UTF-8. So we can essentially get rid of all of these, since we kind of don't need them right now. Of course, we're going to need them in the future, but yeah. So UTF-8, right? So UTF-8 is just a bunch of bytes, which now we can match with self. We can do something like, okay, are you UTF-8, self UTF-8? Are you self UTF-8, right? So are you UTF-8, right? Well, we can implement this later, right? It doesn't matter. So we can implement this later, but let's actually implement the base logic here. So it's actually, instead of having this constant pool count, let's actually have something like constant pool. Or yes, we can call it the pool or const pool, right? Which is just going to be a vector of const info, right? And that's going to be a new vector, right? So we have that, and we can just do constant pool dot. So whatever we put into we do some operations in here, and so that we don't really forget about it, let's actually just do constant pool length not +1 as U16, right? So okay, we have the length, right? And it's probably, yeah, +1, I'm sure, because if it's 0, right, we want to have 1, which internally wouldn't change a lot, but in this case it would. So now what you would probably do is have the following thing. So we have const info 2 bytes, and then have, okay, is it UTF-8, right? Is it UTF-8? In case it is, then we can just kind of extend bytes with our bytes. But before doing that, we also need the length, right? Because the UTF-8 structure, info structure, itself has the U2 length, right? U2 length. So we can extend it by 2 bytes, which is going to be length, as a U16, and this whole thing 2b bytes. So that's kind of cool. And before doing any of that, right, we need to write also the tag. So we need to do tag UTF-8 dot 2b bytes and write the actual tag, because all of them follow, all of the parts of the Const Pool table have a tag, a length, and some bytes. So that's it, right? That's for UTF-8. And now let's actually implement class, which is actually really simple because it's just name index, and we just do something like, okay, let's extend by tag class 2b bytes, and bytes extend by also name index 2b bytes, and that's it. It's literally it, right? So that's it. And then what we can do is, after we write the constant pool count, we can just go from, we can just iterate over all of the elements. So that's element in constant pool, and we just do element 2 bytes, and we can just pass in our mutable output. Right. Alright, so now we extend it by those bytes, and we have the count, right? So that's kind of cool. So what we can do is now just do something like constant pool push some sort of like UTF-8 structure, that's const info UTF-8, and the bytes are going to be just something like what we can just do, we just have just the class, the Java object, so that's our name. Well, the name is going to be output, of course. It should be output because the class name is actually output. Okay, so now that we have these bytes, we can just take this and just have constant pool, probably push some sort of class, which is called the const info class, and the index is actually going to be the last one, so that would be just 1, right? That would be just 1, so that would be name index 1, which as it stands isn't too bad, right? But I think it's actually a lot better if we just had something like a constant pool structure, right? Which would essentially have some sort of body, which is called inner probably, which is just a vector of constant info, right? And what you can do with this structure is just have a function. First of all, we can abstract this away, so now we can just do something like 2 bytes self, and then the bytes we want to extend here. So now what we can just do is take this code and essentially put it in here. So we have, okay, this, okay, get that, get the constant pool count, which is just self inner count, so that's 2 bytes, and then for every element in the inner pool, self inner iter, we can just give it some bytes, right, to convert it to the bytes we want. And what that allows us to do is actually have a function like create, which what it would take is some sort of type, some sort of const info, and it would just return an index, which in this case is 16, because that's what we use for indexes. And that's what we kind of cool, right? Because this code is really redundant. Imagine you have to add more and more to this constant pool, right? That would be very, very, very tedious and annoying. So how about we just do this, right? So just have a create method, which what it would do is actually fix situations like this. So name index, here you have name index, right? The problem with name index is the fact that now the index for that UTF-8 string is like very dependent on where it is inside of the entire pool. So if we add some sort of elements here or add some sort of element here, now we have to remember to change this, right? So what this allows us to do is actually have something like, okay, we have a mutable self, and we just have self inner push info, and then we can actually get the length, which would be our result, length, and return that result, right? And what that allows us to do is just have something like, okay, delete this. Instead of doing that, we just do constant pool create, constant pool create, and we have constant info UTF-8, which would just be bytes of output to vector, which is a lot easier. It's a lot longer here, right? Because it's a lot of symbols, but you definitely can shorten it and make it seem a lot easier to read. So how you would do this is probably something like this, right? And that's it, right? We create some sort of class index, and that index is now we can now take that index and actually store it. So that would be just this class. Alright, so now we have that. We can write out not only this, well, first, right, remember we need to do 2 bytes. So that would be just our mutable output. And we also want to write this class. So that's after the value. We just do this class to be bytes. And that's how simple it is, right? And now we need to do superclass, and the superclass is essentially this. And what do? We take this because it's fairly similar. We paste it again. We do superclass. What is that superclass going to be? It's going to be Java lang object superclass. Okay. And then we can take that superclass and just write it. And now whatever I add between these two, or here, or wherever, isn't gonna matter, because the index is very dependent on just the order of operations, not exactly like before it was dependent on like a lot of other stuff. Like for example, if you added more stuff before your UTF-8 string, now you have to remember to also update the index inside of the name index for the class. And now it's very, very simple. So we have that implemented. Then we have interfaces, which I guess interfaces was just a bunch of b bytes, but we're not going to handle interfaces just right now. So constant interface info, our constant in was it just, yeah, it was interfaces count, which is 0, so we just do output extend 0 as u16 to be bytes, and then we don't need to write anything, so that's 0, and then fields 0, we don't store anything currently, and methods also 0, because we don't really want to have anything right now, right? We have this, none of these are handled, right? And now we get to attributes, which I feel like attributes are something a little bit like more weird in this case, because we have to prep them a lot, so maybe we have to have them above here, or for right now let's actually just write them as 0. Write them as 0, so no attributes at all, so absolutely 0 down the board, absolutely nothing. This is an empty file, right? This should be like a very, very raw version of our class file. So of course it's going to have a few issues, like for example at line 52 we don't use self, okay, and then at line 58 we have an issue with to be bytes. Is that is that something? Okay, so that's just bytes extend, right? And that's just bytes, right? Makes sense. And that should be most of what we have in here. So let's clear again and run it once again. So you have result, which, okay, so now we need to do as u16, and that's it. So let's run it, and then we have vector news expected. Yeah. Okay, so now we need to do constant pool default. So we can just derive default since we have that already done. And if we run it, okay, we run it, I said, a lot of issues. So byte is a at reference, so the data that references borrow is mutable. That's at line 39. Let's go here. So to be byte is a reference, so the data it refers, it cannot be borrowed as mutable. Okay, so that's actually called as out, maybe, and let's actually replace these bytes with out, and these bytes also with out. Alright, that's a very simple fix. And then what do we have? We have constant pool create is mutable more than once within the scope. Second mutable 74. 974. Why is that exactly? Well, okay, so that's a little like annoying. Try adding a local or storing this argument. Well, sure. I mean, like, I don't like this. This is very stupid. You definitely could resolve this without that. Okay, output. So, oh yes, name index. Or yes, let this class equal to that, and then we can just return this class. Come on, where is it? For frick's sake. Okay, this class, or we can just return this. Right, so we just do this. Okay, we just take this, and that's it. And yeah, we just fixed it. So that's it. We can even probably shorten this to just being that, like so. Yep. And that's just Const Pool create, and we just get this class. So that's not too bad, right? That's not too bad. So let's do this for the superclass as well. Superclass, and that's name index, and that's it. So that's just going to be Java. What was it? Java lang object. That's it. So now we just do that. Unclose delimiter. Okay, I guess it's just this. Okay, that's it. Okay, and then oh my god, it complains about semicolons. Sure. I mean, alright. Constant never used. Can I derive that allow that code? Hashtag allow that code. Was it this? Totally. That code. So that's it. And now, if we run it, we have written to output.class. And what do we get? Well, we have attempting to subtract with overflow. That's interesting. Very interesting, right? So we have at line 97. Ah, yes. Okay, so the ID is actually +1. So can't we just do this? I guess that's kind of easier to a certain degree, but yeah. Okay. Now we wrote it correctly, and here we go. So we disassembled it, right? We have Cafe Babe. The version is 55.0. The constant pool count is 5. The access flags are 0x21. Some sort of, so we have this class and then the superclass, but this is all very much incorrect. Yeah, why is this class okay? Okay, so logging is a little wrong, but I'll take it. So we have this, which is the most important one, which means that we did this correctly, right? So that's kind of cool. So we've generated some sort of file, right? But if you try to actually run this with the Java virtual machine, what you would get is actually, oh, right. Error, main function not found in class output. Please define the main method as public static void main, or a JavaFX application class must extend JavaX application. So we need to define this, which I guess isn't too bad. So the first thing you should notice when starting off doing this with Java and its bytecode is these kind of weird descriptors. If you've checked out the disassembly, right, you've probably seen this, which is absolutely bonkers, right? It's absolutely bonkers. How the fuck are you supposed to know that this is actually what you're supposed to be, like, what is this even describing? So let me actually break it down for you. So V, actually, it's not too bad, right? This syntax isn't too bad for describing stuff, but it's essentially the parentheses are, you can imagine as, like, if you open up some sort of like Java file, right? We have like the class. If you have the parentheses, the function, like, let's say foo, right? We have this function. So the parentheses you can imagine as these parentheses right here. And what you get after that is actually a special character. After these parentheses is a special character. So that special character actually indicates the return type. So in case you are returning, in case you are returning some sort of base type, you would find by the way, this is described here, right? So if you were doing some sort of like, for example, char, so if it was, for example, if you had a function called something like bar, right, that return a character, this would actually compile down to, okay, this, and then what is the symbol for character? It's C. So you'd have no parameters, and then C as the return type. Well, okay, you say, what about a function like, for example, add, let's say, where we have something like this, right? We have two integers, A and B, and we have a result, which is also an integer. Well, how do you actually compile this? So what Java ends up doing is essentially just saying, okay, what's the symbol for integer? It's I. So what you can do is just compile this down to, okay, we have an A, which is an integer, so that would be an I, and then the next argument is what? It's another integer, so let's have a dot comma or a semicolon, as people call it. And what do we return? An integer. So actually, if you compile this code, well, this wouldn't compile really in Java. I don't think it would. But if you compiled this, what you would see in the disassembly, actually we can even show you. I can even show you. Let's actually write this add function, and let's just do something like a plus b, right? Let's do that. I'll prove to you that this actually, if we take this and we just if we take this and actually build dem.java with Java C, dem.java, we get temp.class, and if we go ahead and disassemble temp.class by going into here and saying, okay, instead of output.class, let's actually disassemble temp.class, what you okay, that's weird, invalid opcode. So yeah, I don't have all the opcodes implemented, but let's actually go ahead and implement it so you can see, just so you can see. So let's actually minimize this and open up the disassembler and go into source main.s. Okay, edit anyway. So if we go ahead and go to the opcodes, which I don't know if, yeah, I defined them here. So opcode 0x1b, we can find it here, which is iLoad, and then some sort of count of the variables. Well, we can just do something like copy this, paste it once again, and do iLoad, which these are basically like loading some sort of variable from the variable stack. So we have 0x1a, 1b, 1c, and 1d. So that's 0x1a, 1b, 1c, and 1d. So that's iLoad instruction. And now we can actually add that as an instruction, which is called an iLoad count, which is a U8. And we just do the following thing, which is take this, copy it, paste it, and so we have iLoad, right? So let's actually have iLoad, and replace all of these with iLoad, right? So now we have an iLoad instruction, which again it would load, it would tell us anyway, but I guess that's fine. And let's continue with the assembly. And what do we get? We have an unknown opcode of 0x60, which that's actually I add for adding integers, but you can always also just see the fact that we have these kind of like patterns, right? We have the integer load, which we had, right? We implemented that. But then we also have iAdd for adding the integers, right? For the actual function. So now, now we have iAdd, which is just its own thing. And now we just do opcode iAdd self I add, right, and that's it. So, and now if we run it, what do we get? We're missing 0xac, which is I return, integer return. That's kind of cool. Let's do that. Let's do constant opcode I return. Okay, opcode I ret, and that's usually going to be the same as return, just I return, right? So then what we can do is just opcode I ret self I ret, right? And that's it. Okay. And what do we get? Right. Look at the disassembly. As you can see in here, well, it was similar. We thought it was with a semicolon. They actually aren't separated by. Where is this? Let me close this. They aren't actually separated by a semicolon. They're actually just one next to each other. But look at the definition, right? It's an integer. This. An integer, which is this. And then another integer as a return, which is this. Alright, so the descriptors are not too bad. Not too bad. So essentially, what we can now do is just have the following thing, right? So we can go ahead and actually go into here and just close the disassembler that we have set up and go back to actually generating some stuff, because this doesn't actually run currently. Well, we can remove the temp.java and the temp.class. I guess we can actually keep them for right now. They don't really bother us too much, but if we try to build output.class, we have main method not found in class output. Please define the method as public static void main string args, right? Exactly the same as what we had in the example for example hello world, right? So yeah, and not example, it's example with one E. Example hello world class, right? So what do we have for the main function? Well, the main function is actually with a descriptor of u, so you start with the arguments, right? It's a void function, and it has these access flags, which is 101, which is a public and a static function, right? It's public static. Makes sense. So how do we actually define that? So inside of source main arrest, we should define public static. So and a lot of other attributes. For right now, we probably just need public attributes. Okay, it's not here. Attributes maybe. No, what it was, access flags, right? This stuff, right? Let's actually define that. We're probably not going to be using all of it, but that doesn't matter. So we can do constant this with that, and that's just equals, and that's equals, and that's equals. That's equals as well, that's equals as well, that's equals as well, that's also equals. And then we can just remove these type of enumeration, declaration of annotation, or we can just, you know, keep them as comments. Okay, okie dokie. We can then do this, then have the comments, and of course we need a semicolon at the end, and probably give it a type as well. That's kind of important. So Okay, this, and then one more space, and that's it. And here we can just add a few spaces to make it work, right? Or we can just, you know, remove these types of spaces and just do that. Okay, so we have that. We have the access public, access final, super, synthetic, and whatever. So does it have like static? I'm not sure, right? So static. So okay, so we have different types of access flags. Now we also have 0x08, which is for public, private, final, and all of that stuff. So that's a little bit weird, right? That's even more declaration that we have. Well, we can just kind of redeclare them, and if anything happens, we kind of don't need to declare probably this. So now we just do constant, and then this. Okay, and that's kind of very easy to parse. We just comma, and then we just do space, this, and then equals. So what do we need? We don't need transparent, synthetic, volatile. Well, volatile we can keep, final we can keep, static we can keep, private and protected. That's fine. So what are all of these? Well, access is your attributes, and their access flags are all usually just a U8. So we can just define them as a U16. Not a U8, it's a U16, right? I'm sorry. U16, and we have this, right? So now what we can do is just essentially have what we can have a function called the main function now, which we can define inside of the methods, which now we need to actually have like a method pool, and all that kind of stuff. So right, that's, yeah, I mean, yeah, we can have that, sure. A vector of method info, which method info we can also yank from Java Disassembler source main.s. We can take directly from where we had it. So it's method. Where is it? Do we have method anywhere? Hello? Method info. Okay, this, undo. So it's this, which we can yank and place in here. So that's it. And then we just do implement the method info first, right here. And we probably can just have something like 2 bytes, which would just take in the self, and to take in the mutable bytes of the U8, right? And what it would do is just take the flags, self access flags, dot, and that's 2b bytes. After doing bytes, extend by 2b bytes, and then we have the descriptor index, the name index, and so on and so forth. So now we have the name index. Okay. More stuff, and even more stuff. And that's it. So then we can extend the name index, the descriptor index, and then the attributes itself. So attributes are now going to be a little bit weirder, right? We're going to have attributes dot 2b bytes, and for right now they're going to be 0. So I guess we can just extend by self attributes length as u8 to b bytes, like so. So then we can just do that. So we have this working. We can then, for now, we can just assert that it's false. So we can just do something like, okay, 0 as u8, so this has 0 attributes, and that's it. And then the method pool is essentially just going to be fn to bytes. Self and then bytes, which is going to be a mutable vector of bytes. So then we can just get the pool and then just write, what was it again? It was essentially just 0 and that. So we just do self inner length as u16 to be bytes, and now that can actually extend bytes. So that's bytes extend this, and then we can just do for method in self inner, we can just do method to bytes, and those are bytes, and that's it. So yeah, now we can have the method pool, which should be declared above here. Let mutable method pool, and I'll explain why in a little bit. So that's a method pool default, which is just a hashtag derived default. Okay, and then let's actually go back to the documentation to see where it was. So it was, the last thing was methods. So before the attributes, it was methods. So here we can actually probably do something like method pool to be 2 bytes. And that's going to be on our mutable output. Okay, so we convert that to bytes, right? And we write that to the file then. And why do we do that here? Well, it would be very handy if we had a function that was like method create that would just take in the mutable method, or maybe even just method pool create that sort of thing that's called like, I don't know, maybe we can do something like main, right? Main, and we can give it some attributes, like for example it's a public static, so we probably, yeah, do action public or the action static, right? So that's the access flags, and then the other stuff, so that would be just public, static, and whatever else we have in here, right? And the actual descriptor and whatnot. So then, right, that would be very neat, but to do that you have to be able to access the constant pool, and but the constant pool has to be built before the method pool, after the method pool, because somehow it has to know its length, right? So because at this level we have to know already what the constant pool looks like, and we can't really build it here because the constant pool already has been written to the file, right, or to our bytes. So we have to first write and create the methods here, which would in turn change the constant pool, which, right, that would lead to other stuff within it that would lead to, at the end, having those bytes for the constant pool, right, be written to the file. So for now we don't have this, but to be able to achieve this we also have to have some sort of access to the constant pool. which the single easiest way you could do that is probably by putting everything in a structure, which luckily we already have, which is called JavaBody, right? JavaBody. And as you can see, a lot of the stuff is actually shared, so that makes me think that we might be leaning towards actually having a library that is common amongst Java, the Java disassembler, this and maybe future projects, right? So maybe, we're not sure just yet, but yeah, let's have JavaBody. And now instead of doing that, we can just do something like, right, we can just do fn2 bytes, which would take in self, and it would take the mutable bytes, or in this case out, so that we don't have to modify it too much. So it's out mutable vector of u8, right? And yeah, that's it essentially. Just that we're going to have essentially fn new, which should be just self, right? And its result, which is going to be something like self, not self default, and we're going to change some stuff in here afterwards. What does it to do this? So right, we have that done. Now we need to just take all of these bytes and stuff, this stuff that we've already done, and just this and put them inside of the function, right? It's that simple. Okay, so some of these are not very needed, but I'm going to still keep them. So yeah, now we don't have to borrow output as mutable because it's already a mutable reference. Okay, and then we can now do self magic, self minor version, self major version, self constant pool, which I guess here we can fill up. Maybe we have to do something like, yeah, maybe we have to create the constant pool here, or yeah, we have to create it here, so then we can not here, right? It's not created here, it's created in here. So that's why I put it to do, because we need to change it in here, this stuff in here. So essentially constant pool, it's actually going to be self constant pool, and that's self major version, and that's self access flags, which I guess self access flags, result access flags, that, and that's one of the things we do. Result constant pool, that's actually already initialized, right? And then we do result constant pool create, result constant pool create, and it's going to be result superclass, and result this class to be result create. Okay, now this is the method pool, which we don't need to initialize the default anymore, right? And that makes it a lot easier actually. Feature self this class to be bytes, self this class to be bytes, and self access flags to be bytes. All right. So now we have this, right? That makes sense. That's kind of cool. We also probably need to initialize some of the stuff, like for example the magic number being Java magic, the minor version being Java minor, the major version being Java major, and so on and so forth. And that's it. So not this, right? Let's actually test this. We probably are going to fail miserably because we have quite a few issues, but yeah. So line 18, redefinition of constants. Final. Already have it. Makes sense. CLS. Cannot find attribute info in the scope. Not found in the scope. Might be missing a type parameter. No. Line 83. Okay, so for right now, I don't think we're going to tackle with attributes, so let's just comment them out. They're a little bit of a pain in the butt, but field info, also something we're not tackling with, so we can disable that, and interfaces also we can disable. So right now we only just have the method pool. So instead of a method pool, it's now just methods, which constants. That's actually, that makes a lot more sense. Right. But it's inconsistent with the other API, so we'll just keep it this way. Or maybe not. I mean, sure, let's actually have some sort of consistency between APIs. Right? Constants. So it's constants to be output, because we have methods and constants, which is a pool of a single constant rate. So okay, hashtag drive debug. Oh my god, can't you just do this yourself? Also attributes, we don't tackle with attributes anymore, so we can just derive debug, also have it, have this, also derive debug, and that's fine. So we have this CLS cargo run, and then constant pool at 127. That's constants and constants. And now that's probably going to complain something about lifetimes again. Clear, and then run it again. Yes, occurs. So at line 1000. Oh, it's an iter, right? We just iterate over them instead of doing that. So that's just cool. So mutability not needed. So now we need to just have some sort of JavaBody. Mutable Java, I guess body equal to JavaBody, which is equal to JavaBody. Yeah, so that's it. And then we just do body 2 bytes, and that's mutable output. And that's it. So we get this. No need to be mutable. Okay. Sure. So then we run it, and we get the output.class. So now it should look the exact same, given we haven't changed anything. Okay. Let's actually clear again. And yeah, it looks the exact same. So that makes sense. Let's now actually add the attributes that are needed. So I think attributes are kind of like one of the few things that we kind of want to do soon enough. Let's do that actually. So, well, we can do something. We can do something like attributes, define them at the top or lower, I'm not sure. We can define them here, which derives from an attribute, which are these things, which require other stuff and a lot of care and attention, which I don't have right now. Okay, I need to copy so much stuff. It's insane. Okay, code log. Also, copying the log functions, I'll probably do that afterwards, but yeah. Well, we don't really need to tackle with this yet, but I guess I'll do it. Oh my god. Wait. So much stuff to be done. So we have a code exception now, which code exception, where is it defined? Code exception. Here it's defined here, so let's take it. Yank cool code exception and attribute info, which is, loops back into this. That's it. So makes sense. And that should be all we need. Align number table, that's fine. We can just remove this comment since we don't need it. So now methods can actually have this. And I guess that's very much easy to implement since 2 bytes. So and then since this is very like we've already done this a lot of times, not so. I feel like it should be fairly straightforward to implement. So we have mutable vector view 8. And then you just have match self. In case it's a code block, we need to call its code block. So we have a bunch of functions that are left for it to do. Let's actually just do something to do. Attribute 2 bytes, and we'll go through with what we need. So that's attribute info 2 bytes, and then code block, which would require also 2 bytes, also requiring a bunch of stuff. We can just do code block 2 bytes. And then instruction 2 bytes. Oh my god. Okay, let's take this, put it here. Instruction, 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 and that's and call exception as well. That also requires to do. It's to do. I know it's unreachable right now, but it doesn't matter. Right, let's go through with it. So let's accept that it's implemented, right? What do we do? Well, we can just get the length of the attribute, so self attributes length, and that's it. And then we can just do for attr in self attributes attr 2 bytes, and those are the bytes, and that's it. Which is actually the same as the JavaBody, which is kind of cool. Right, instead of that, now we replace it with this, which we can probably abstract in a attributes pool, but I don't think it's needed, at least not yet. So for now, I'm going to just have this. Okay. We have attributes, and that's it. And we do 2 bytes on the different attributes that we have, and that's it, I think. I wouldn't say we have anything else that we need to do. Right. Currently not. So let's run this. And yeah, we have a lot of issues, So 86, okay, bytes, right. Let's actually take this definition, paste it here, yank, paste, shift V to shift V, paste, shift V, yank, and shift V, paste, shift V, yank, shift V, paste, shift V, yank, and that's it. COS really quickly. Let's actually remove all the non-camel case warnings. Go to 0. Essentially here, hashtag allow non-camel case. Right. And then we have bytes. Cannot find bytes in the scope. So that's at line 225, right, that's output extent. And that's output extent by the output. So I've already been recording for quite some time, and I think after we finish this one, let's take a quick break. And attributes unknown field, yep. Quick break. And okay, attributes iter, and of course this self attributes at line 166. Smokes. Okay, that's it. So unused variable. Well, I guess we will allow unused variables quickly, very quickly. Go to 0. Quick. I said quickly. Hashtag allow unused variables, right? And that's it. So yeah. So we shouldn't get any warnings, and we write to the output file, and it shouldn't be any different since we cannot really change anything. So yeah.